Welcome to our lesson on linear reductions and exponential growth. So, first let me start by asking you, how do bacteria reproduce? Well, the answer is binary fission. It means that one bacterium turns into two bacteria. Then, two bacteria turn into four bacteria. Four bacteria turn into 8 bacteria. 8 bacteria turn into 16 bacteria, and so on and so forth. If these values were to be plotted on a graph, you would obtain what is known as an exponential graph. Here, as you can see, it's 2 to the x power. Unfortunately, in the real world, the number of original bacteria present may not be known. Also, the frequency at which they reproduce may also be unknown. However, what is known is that bacterial populations and other such similar phenomena can be modeled by the equation y equals ab to the x power. So let's look at an example. A new respiratory virus is spreading through a city. Sounds familiar. The table below shows the number of infected individuals on a weekly basis. So we have the time, t, that is measured in weeks. So week 1, there were 15 individuals, I, who were infected. Week 2, 46. Week 3, 133, and so on and so forth. So it is believed that the number of infected individuals is modeled by the formula I is equal to I naught times r to the t power, where I is the number of infected individuals, I naught is the initial number of infected individuals, r is the basic infection number, and t is the time. Just a couple of notes here. I naught is the old-fashioned way of saying I sub 0. Naught is the old English word that means 0. N-A-U-G-H-T. R, our basic infection number. That is the amount of persons that are expected to be infected by one individual who is already infected. Or in other words, how many people are likely to be contaminated by one person already contaminated with this virus. So we have to determine the values of I naught and R. So how do we go about doing that? Well, if we plot a graph of I versus t, we get this curved graph as we see here. But how can we use this to determine the values of the initial amount of people that had the virus? And how can we use it to get the infection rate? Well, we would need to see what the amount of people was at time 0, when the time in weeks was 0. We can get that from this graph here. As we can see, it says at time 0, it's 5 persons. But how could we get the rate? Well, the rate would be the gradient of this graph. But if it's a curved graph, how can we get that? Unfortunately, for this curved graph, we can't differentiate it. So instead, we have another technique, what we call linear reduction. So our solution is to take our original formula and convert it to a linear form by using logarithms. So our formula is I is equal to I naught times r to the t power. Taking logs of both sides and then applying our laws of logarithms, if we are multiplying I naught times r to the t power, then we can add those two logarithms. The next law that we can apply here is that we have r to the t power. So since it's to the t power, that t can go to the front and multiply times the log of r. Next, I want to just rearrange this a little bit, and you'll see why in a few moments. I'll just rearrange it to have t log r to the left, and then plus log of I sub naught. Comparing this to y equals mx plus c, we'll see that the y is equal to the log of I, x is our t value, the time variable. Our gradient m will be equal to the log of r, and then our y-intercept c is equal to the log of I naught. So, to work this out, we need to find the log of I, because that is going to be our y values on our y-axis. So, to do that, we find the log of I. So, the log of 15 is 1.18, the log of 46 is 1.66, and so on and so forth to 2 decimal places. Fortunately for us, x is just simply equal to t, so we do not find the log of 1, 2, 3, 4, and 5. Our time values simply stay as they are. Now we plot these values, they appear to line up in a straight line. And if we were to draw our line of best fit, we would indeed see that they do line up in a straight line. So, to find our R value, we would need to find the gradient M, and to find our I naught value, we would have to find the y-intercept value. The first one that we can find quite easily, right from the graph, is our y-intercept value. We just simply look at our graph and see where it crosses the y-axis. Looking at our graph here, we see that it goes up by increments of 0.2. So 0.2, 0.4, 0.6, 0.8. Our line of best fit crosses the y-axis right in between the 0.6 and 0.8. Therefore, that is 0.7. So if that is 0.7, that means that the log of I naught is equal to 0.7. Hence, raising both sides of our equation to the 10th power, right? Then the 10 and the log of I naught are going to cancel each other out because exponents and the logarithms are the inverse of each other. So we're left with I naught is equal to 10 to the 0.7 power. And when you use your calculator, that gives you 5.0 to 1 decimal place. That agrees with what we got before when we look at our curved graph. Next, the value of R. So we need to find our gradient. To find our gradient, we'll then need to draw our triangle. We should not simply use the values that lie on our line of best fit because theoretically, those values may have some error in them. It may have been the case that not all cases were reported, right? Not all new infections were reported. It may be the case that there were some false negatives, right? Some false positives. So it is not the best thing to use those values that were plotted. The best thing, in theory, is to use values on the line that were not any of those that were plotted. So our gradient M is y2 minus y1 over x2 minus x1. Looking at our upper points, the y value is 3. And the lower point, the y value is 1. So we have 3 minus 1. For our x values, this is 4.8. And our lower value correspondingly is 0.6. So we have 2 divided by 4.2, which gives us 0.48. So the log of R is equal to 0.48. To find R, we will then raise to the 10th power. So R is 10 to the 0.48 power, which is equal to 3.0 to 1 decimal place. Hence, the formula for the number of infected individuals is I is equal to 5 times 3 to the t power. This means that initially there were 5 infected persons in this city, and on average, 1 person infects 3 other individuals. Remember that R was the basic reproduction number, or you could say the infection rate. So 1 person infects 3, those 3 infect 3 each, and it grows exponentially like that. So that is the end of this lesson.